So now we want to talk about the method. Now we want to talk about the equivalence principle, which we have started. Let's talk about the last time. So the last time we have discussed the first form, the first form of the equivalence principle. So our first postulate, which was that the inertial and heavy mass are the same. Okay, so they have intrinsically the same mass as a fundamental postulate of physics. This is our fundamental case. And so now, on this, we can build the following version of the equivalence principle, which there are different versions of the equivalence principle. And we want to start with the weak equivalence principle. And this we can explain with some drawings. So we consider 4 physical situations. Okay? So the first situation is
heavy mass is gravitational mass.
The gravitational mass. So the first one is we have a rocket in which somebody makes experiments. Einstein, all right. So it's this rocket, and so this has a constant acceleration a. All right. Okay. So this is out somewhere in space, far away from any other influences. There's a rocket with constant acceleration in which somebody makes experiments. The second case is we have the same rocket without any acceleration, just floating around. The third case is that again we have our rocket, but now it's grounded on Earth, standing on Earth before launch, not doing anything. And the fourth case is that somebody has been digging a big hole into Earth, in which our rocket is now falling. En el segundo, sí, en el segundo caso es un sistema inercial. Okay? So, aceleración uniforme, un sistema inercial. La aceleración del campo gravitacional de la Tierra, pero no moviendo relativa a la Tierra, y aquí en free fall. Okay? And so, what the weak equivalence principle says is that the situation 1 corresponds to situation 3 and 2 to 4. What does that mean? So 1 and 3 and 2 and 4.
What is 4?
4 is when the body is in free fall in the gravitational field. Okay? And so what does equivalent mean? So equivalent means if you make some experiments In particular, and it depends on the precise formulation of the equivalence principle, what kind of experiments are allowed, if it's just mechanical experiments or also experiments involving electromagnetic fields or any kinds of other fields, other interactions. So we make experiments within the rocket, and so we make what we call local experiments. So experiments which are confined to a small region in space and a small region in time. Okay, so experiments which do not test the behavior over long, large reaches of space and time, but which are essentially experiments local essentially on a point and in a neighborhood of space-time. So if we translate it into the mathematical language, we talk about a point and a neighborhood, and this is only of size epsilon. So the first thing is, these things are consistent with our day-to-day experience. Maybe more or less consistent with our day-to-day experience. So the first one is we are in a constant acceleration, and the second one is standing on Earth. And so we can imagine that, so if we don't, how can we tell the difference between these two situations? Well, looking out of the window. Looking out of the window tells me I'm standing on Earth and not in a spaceship. But if the windows were closed, I cannot tell. Okay? And so what Einstein's postulate says is I cannot, not that I cannot tell because I am somehow a bit stupid or I don't have enough experimental equipment, okay, or not enough money. It's fundamentally impossible to tell these two differences by any experiment which I can do. At least if it's a small experiment confined in a certain amount of time. If I could do the experiment over a long period of time, let's say a period of time during which the rotation of the Earth maybe is important, okay, or if I wait a whole day maybe, then maybe there's an effect that I can measure because I can measure the somewhat more complicated acceleration around the sun or whatever. But in a small neighborhood I cannot. Okay. And the second one is here I'm in some inertial system. Once I'm in an inertial system where there's no gravitational field, and once there is a gravitational field. And so an example that is not quite the same, but maybe more realistic is if I'm in some train. Of course, there's a gravitational field, but only in one direction. And so I cannot detect the relative motion, say, of the train in the xy plane. I can only and the second one is where, so let's say my elevator has lost the cable. I'm in free fall, and again I would not be able to tell the difference between these two situations. Right?
No sería el 1 con el 4, porque free fall tiene aceleración constante, ¿no? Que es que in the 4 you have
there is a right. So there's an acceleration which the rocket is accelerated relative to the center of the Earth, for example, right? But you cannot feel it. So, I mean, if you can feel the acceleration of the Earth if you are not moving, then you feel the force of the ground that holds you from falling further. But if you feel freely falling, so we don't usually do this, but I think so it's easy to refer to it if you're in an elevator that just starts moving, right, or just before stopping, then you somehow feel like book, right, and so if the elevator would really be cut loose and you fall, then for at least a short amount of time you would not feel any forces. Whereas if you jump out of an airplane, you maybe with what do you call it? Diffusion pressure. Usually